Hello and welcome to my video demonstration on CleverCat, a prototypical IoT device that uses machine learning models to detect cats and a servo motor powered dispenser to dispense feed for them based on feed schedules defined by the cat's owners using a web app. The device then sends back photos of the cat that can be seen updating on the web app in real time, and the user could then tag these images with their cat's names, and when enough of them are gathered, a new machine learning model could be trained to differentiate between different cats and allow the user to schedule different feeds for each. There are two main parts to the system: the feeder device itself, which is a Raspberry Pi running a Python app, and the various services, which are all running on a Docker network on an Ubuntu VM. The parts used for the feeder are a Raspberry Pi 3 Model B, a high-torque MG996R servo motor, a Pi camera module 2, and a breadboard and some buttons that were used to actuate the motor when testing its construction. Two main challenges were encountered when constructing the dispenser, and both were related to the feed itself becoming stuck in some way. The first challenge was clogging, where the feed would pack up tightly against itself and cause the hopper to become clogged. Initial designs used a funnel system to funnel the feed into an opening that was covered by a motor actuated gate, but even pretty wide openings of 3 or 4 centimeters would become clogged, and having the opening any wider would have put the gate under too much strain from the weight of food it's holding in. The final iteration of the design uses a rotating collar that exposes an opening cut into the cylindrical hopper it surrounds. This allowed for a bigger opening, which led to a much lesser chance of clogging, but probably some disturbance of the feed, such as vibration, would be required to prevent against all clogs. The second problem was feed particles jamming in the opening when being closed. This was more or less solved by cutting the opening in the collar at an angle to the opening on the hopper, so that there was a sort of shearing action when closing, preventing two long sides meeting where lots of particles are trying to escape. Some flexibility and tolerance was also built into the plastic collar to prevent the motor from seizing when clogs did happen. Before continuing to look at the software, let's take a quick look at the main functionality of the feeder in action. I'll first show the dashboard screen. Then, instead of using a real cat, I'll hold this picture of a cat up to the Pi camera. The app will then detect the cat and check to see if the cat is due a feed before dispensing the food. You can then see on the dashboard screen that it is being updated with new photos of the cat. Now looking at the feeder software. There's a main.py driver script that just loads some environment variables, instantiates the main feeder class, and continuously updates the feeder. The backend service Pocketbase uses user authentication instead of API keys to give clients access. I imagined a flow where users could create a new feeder on the web app and be given a new feeder ID. They could then log into their account on the feeder and register the device with this ID using some sort of Bluetooth interface to the device that would also make it possible to connect the device to Wi-Fi. A special default user ID is also required to gather associated default records and files from the backend. The main feeder class is composed of and manages all of the device's objects. Its init function sets up the Pocketbase client and authenticates the user, gets some default info that is required by the ML model, instantiates the camera and dispenser classes, gets its own record data from Pocketbase, gets the model record from Pocketbase, downloading a new model if necessary, instantiates the pet detector class, populates a dictionary of feed schedules for each pet, before finally setting up real-time subscriptions to Pocketbase's feeders and feed schedule classes. Lots of methods, mostly private in nature, are defined in the class to keep the feeder updated. There are also some static methods for general conversions, and 2 event handler methods that are used to handle real-time subscriptions. There is one main update method that gets called in the while loop of the main script after all initialization is completed. It takes an image using the camera object, checks this image for pets using the pet detector. If a pet is seen, it converts the image to bytecode, gets each detected animal's ID as well as its bounding box within the image. It then uploads the photo and detection record to Pocketbase. After that, it gets the pet's feed scheduler and uses it to determine the amount of food due for that pet. If feed is due, the dispenser will dispense the required amount, a feed record will be uploaded, and finally the feed schedule will be updated. The feeder class makes use of a couple of classes written specifically for the device. There's a camera class that takes care of initiating the camera capture and taking, converting and saving images. A dispenser class sets up the servo motor and offers a method to dispense a certain amount of feed based on feed rate. There's a feed scheduler that takes the time of a pet's last feed and the schedule itself and offers a method to return the amount of feed due. There's then the pet detector class to load and initialize a TensorFlow model stored locally and offers interfaces to detect pets from an image file or a NumPy array. Here's the requirements.txt file for the device. I'm running the app in a virtual environment and have modified the device's rc.local file to run the app on startup. Now moving on to the back end, the Pocketbase service is a self-hosted Firebase alternative that runs a real-time database, file server, user auth management, and admin dashboard in a single binary file. It offers a HTTP interface with wrapper SDKs for JavaScript that I'm using with the web app, and an unofficial Python library that I'm using with the feeder device and ML training service. I've set up database collections for users, feeders, models, pets, pet photos, feed schedules, and feeds. And I've set up API rules to ensure that they can only be accessed or modified by users that are authorized to do so. I've also set up an SMTP service I created with Google to work with Pocketbase. This sends emails to the user prompting to validate their email address when they register. The CleverCat web app, which is in a pretty basic state at the moment, was created using SvelteKit, Tailwind CSS and Daisy UI and is running on Node.js. It offers users options to register, log in. I'll log in here now. There's a dashboard showing all available feeders with options to add a new feeder or view more detailed feeder information, including the current model's info and the pets it can detect, the details of the feed schedules for each detectable pet, and the details of the last feed dispensed for each too. Note that this edit button is just a placeholder for now. We can also view and add new pets and see a paginated result of photos taken, which will eventually give options for users to tag photos with their pets' names so that new machine learning models can be trained to recognize individual cats. This page also has a real-time connection to Pocketbase, and as new photos of detected cats are added, the page is automatically updated. There are far too many files in the web app to demonstrate them all here, but I'll show a few key ones. The first is this hooks.server.js file, which contains the handle function that gets called on every request to the server. It uses a cookie sent from the client to instantiate the Pocketbase object, which can then be used for any of the server-side requests to Pocketbase using the internal Docker network URL to fetch or create data. A cookie can then be created to send back to instantiate any client-side Pocketbase instances, as is done here in the pluspage.svelte file for the paginated photos page, where the external URL for Pocketbase is used to create the Pocketbase instance after the page is loaded. It then sets up a real-time subscription to the pet records collection, which uses the handle pet photos events function to update the page when a new record is added. The subscription is then ended when the user moves on to another page. The last service to look at is the model training service, which is still very much a work in progress and not yet deployed. It sets up a FastAPI HTTP app as well as an internal connection to Pocketbase, this time authenticating as admin, before creating a post route, which takes a list of the pet IDs to train the model on. This route then gets all the photo records for each pet and downloads the associated photo, randomly designating either training, validation or testing labels to each before appending all the required data to a CSV file in the format TensorFlow expects. The app then trains the model and evaluates it before saving it as a file, which will then be uploaded to Pocketbase with its own record. All services are running on a Ubuntu VM in OpenStack. I've set up a domain server on Namecheap for DNS entries with subdomains for the web app and Pocketbase. There's also a traffic reverse proxy running on the VM to manage routing to the different services running on the VM. And it also generates SSL certs using Let's Encrypt, so all external interfaces to the services use TLS and HTTPS connections. There's a Docker file for each service, and they can all be easily deployed using this Docker Compose file, which builds all images if necessary and then creates a container instance for each using the settings provided. Finally, I've created a GitHub Actions workflow, which creates a Ubuntu runner that SSHs into the VM, pulls any changes from GitHub, and rebuilds and redeploys any changed services using Docker Compose. This workflow runs anytime something is pushed to the main branch. Okay, that's it for this demonstration video. Please do get in touch if you want to talk about it. Thanks for watching.